Let's talk about sensory systems. There's quite a sensory collection there in that illustration, isn't it? You think of what's happening all around you all the time. You've got touch sensations, you've got things you're seeing, things you're hearing, things you're smelling. Your body is constantly getting a ton of information from the outside world. How does that work exactly? What do you do with it? How do you process it? That's what we're going to look at right now. Let's start by talking about the five senses. They told you in kindergarten you had five senses. Well, like a lot of the stuff they told you in kindergarten, they lied to you. They just flat out lied. Didn't even blink when they did it, did they? Let's see what senses we can find. How about this? Yeah, sight, vision, whatever. Okay, how about this? Yeah, we can hear people. I don't know what that means. I did a Google image search for hearing, and that's what showed up. Taste, right? You can taste things. Yeah, smell. Those are professional smellers, by the way. They're highly trained and they make a bunch of money. Maybe we'll talk more about that later. What the hell is this? Caution, this sign has sharp edges. Do not touch the edges of this sign. Also, the bridge is out ahead. Yeah, touch. Everybody knows you have touch. You have a sense of touch, right? No, you don't. No, there's no such thing. All right. Informally, sure, just among friends, we can talk about touch. I've used the word touch several times throughout. Now it's time to get technical. There's nothing exactly that's touch. Let's see if we can figure out what's going on. How about this? Can you tell whether something's hot or cold? Yeah, you can. You have a sense of temperature. How about this? Can you tell when something hurts? Yeah, you can. How about this? Can you tell whether you're about to fall over? Yeah, you can. What about this? You know what that is, of course. That's an Arizona stretch limo. Stretch. That? Have any idea? They train pilots. Acceleration. Can't you tell whether you're speeding up or slowing down? I mean, even if your eyes are closed? Like in an airplane. This happens all the time. My wife and I are flying someplace. Airplanes travel like 550 miles an hour. As you get close to where you're going to land, they start slowing down. They go down like 525. And whenever that happens, I tell my wife, we're in our descent. We're going down. Well, I says, you don't know that. And then 3 seconds later, over the intercom, you hear the pilot. Ladies and gentlemen, we are beginning our final approach into Denver. My wife says, how did you know that? And I'm just like, how did you not know that? Yeah, you can tell. You can tell whether you're speeding up or slowing down. Pressure, yeah. Vibration, yeah. Itch. So look at this. All of those are senses. In other words, if you can detect it, it's a sense. So how many senses do you have? Well, we can count here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. You have at least 12 senses. And there are others as well. Pressure, you have several kinds of pressure, like barometric pressure, osmotic pressure. So you have a bunch of senses, many, many more than 5 senses. So throw away that garbage about 5 senses, okay? You have lots of senses. There are lots of things you can tell about the world around you. So sensory receptors provide input to the nervous system. All the way back when we started the nervous system, we said that the nervous system had 3 basic components. You had input, integration, and then output. In other words, your brain and your spinal cord need to know what's happening in the outside world. How do they know what's happening? Through your senses. Senses are incredibly important. That's the only way you know what's happening out in the world. Your central nervous system needs to know what's going on so you can make good decisions about what to do next. So senses are pretty darn important, okay? Receptors can be classified by location. So exteroreceptors tell us about the external environment. So in your skin, you have receptors for pressure and pain and temperature, telling you about the outside world. We also have interoreceptors. So remember, like we said with the glossopharyngeal and vagus nerves, you have baroreceptors in the arteries. They sense the pressure inside of your body. Hypothalamus has osmoreceptors, detect osmotic pressure. You have pain receptors in your organs as well. So those are interoreceptors, telling you about your internal environment. And proprioceptors tell us about our own body movements and our own position in space. Like I've said several times, if you have to look down to see where the brake is before you can step on the brake, then please don't drive on the highways at the same time I am. Proprioception, we know where the brake pedal is. We don't have to look. Proprioception, we know where our body is and where the brake pedal is. So we can also classify by not only location, like we just did, or by stimulus type as well. So, and make sure you know the types of receptors listed in the table on the left. I'll ask you about these on quizzes and exams, all right? These are basic terms, and you can know them, all right? So let's take a look. Be unique varieties of each type of receptor. So mechanoreceptors, mechanical pressure, vibration, touch, so to speak, even though we said there is one, pressure, okay? Thermoreceptors, heat, all right, cold, temperature. Nociceptors, so that might be a new root word for you. That means pain. These are pain receptors. Photoreceptors detect light. That's what you have in your eye. Chemoreceptors on your tongue, in your olfactory epithelium. Taste and smell are both chemical senses. Osmoreceptors, osmotic pressure, body fluids. Maybe you're not even sure what osmotic pressure is. We talk about that a lot in Bio 202 because it's a big deal. It has to do with the amount of solutes in a fluid. So the more solutes there are in a fluid, the higher the osmotic pressure. You should have learned a little bit about this in Bio 156 with hypertonic and hypotonic solutions. That all has to do with osmotic pressure. Taste and smell both involve chemoreceptors. They have different specific chemoreceptors, so that's what I'm saying. Just because something is a chemoreceptor doesn't mean it detects everything. There are different kinds of chemoreceptors. So the list on the left is just kind of a starting point. There are many subtypes of each one of those, possibly. Okay, adaptation. So you know how like when you first walk into a movie theater from, outside and everything, you can't even see where you're going, you're like bumping into the chairs and stepping, part way on the step and part way off and falling into people and having to apologize and stuff. But after you've been inside for a while, you adjust and you can kind of, you can now see. Yeah, so senses have adaptation. They change in response to the stimuli. So sensory adaptation is decreased sensitivity to a sensory stimulus when with continued exposure. So receptors vary in their rate of adaptation to a stimulus. Tonic receptors adapt slowly. So they continue to respond for the duration. All right, so look over here on the left, you can see tonic receptors. There you see a stimulus, all right, so something, whatever, pressure on your arm. Then you can see the response, all right, the change in the membrane potential and the number of action potentials generated. So a tonic receptor, it responds when you first come into contact with something, and then it continues to respond as long as the stimulus is there. In contrast, we have, those would be nociceptors and proprioceptors, for example. So nociceptors, if somebody, has lit a match and sticks it on your arm, you need to know that it's still happening, all right? So those pain receptors don't turn off. They don't adapt very well at all. They keep sending pain signals as long as the thing that's causing the pain is still there. Phasic receptors adapt differently, all right? Rapidly, sorry. So notice in the diagram, there's the stimulus again. They respond at the onset and then at the offset, all right? So they send some action potentials at the start and some at the end. In other words, there are some sensations that are not critical that you keep being reminded all the time. You just need to know that something happened, and then you don't need to know about it again until it changes, until it goes away, all right? So a lot of mechanoreceptors, like touch receptors. So, think, right now, until I brought this up, were you aware of the fact that your clothes are touching your body? I don't think you were. If you said you are, you're lying, and you know it. But when you first put your clothes on in the morning, or whenever you got up today, that's fine, I don't care. You felt the clothes go onto your body. And then, these touch receptors, these pressure receptors, are phasic receptors. They stop responding. You don't constantly need them to keep telling you, yeah, your clothes are on, yeah, your clothes are still there, yeah, your shirt is still on, yep, your shirt's still there now, yep, okay, right, now your shirt is still there. No, we don't know that. Well, we do want to know if somebody is starting to take our shirt off. That would be something we would want to know. So they fire at the onset and then at the offset. So they fire at the start and then when the stimulus goes away. Those are phasic receptors, okay? There you go. Vision, we have rods and cones. Are rods and cones tonic or phasic? Which are they? Yeah, they're tonic. So they continue to respond to light as long as it's there. So, okay, let's talk about sensory systems, general versus special senses. This is an important distinction. I'll keep reminding you of this. If you can sense something, first of all, you must have a receptor for it, all right? I mean, that's what it comes down to. There are things out there that you don't have receptors for. Like, when somebody, makes a call on their cell phone, can you sense? Because there are waves. There's electromagnetic energy coming from that cell phone. Can you sense it? No, you don't have receptors for that, okay? Sensory systems classified as general or specific, all right? General senses are pressure, temperature, pain, stretch, itch, vibration, proprioception, and many, many others, okay? General senses, we call them. Receptors for general senses are simply modified dendritic endings of somatosensory neurons. They're basically just dendrites that sort of dead end wherever they're supposed to pick something up, and that's all they do. Special senses, and these are the ones, and these are the only ones, so get these down: vision, hearing, smell, taste, and balance. And there are really two kinds of equilibrium. We have static equilibrium and dynamic equilibrium, what we normally just call balance versus acceleration. So there are really 5 special senses, or 6 if you want to count the 2 different kinds of equilibrium. Now, why are they called special senses? What makes them special? They didn't ride a different school bus. Receptors for special senses are unique receptors housed in complex sense organs, and each one has its own type of receptor. So like for vision, what are your special sensors for vision? Yeah, you have those rods and cones in your eye. What about taste? What are the special receptors for taste? Yeah, you have taste buds on your tongue, okay? So each of the special senses has its own special receptor, whereas the general senses, again, are basically just nerve endings that dead end wherever they're supposed to pick up information. Which one of those is not a special sense? That's not a special sense. The others are, okay? All right, let's talk about general senses and free nerve endings. So, first order sensory neuron, remember we talked about first order, second order, and third order neurons. First order neurons go from your skin to your spinal cord, all right? And notice they're just free nerve endings there, just dendrites, okay? So like temperature, it's just basically dendrites that dead end in your skin, and in this case they're receptive to cold, so they are cold receptors. Sensory receptors classified by structure. Free nerve endings are bare dendrites. They're called non-encapsulated, all right? Most are non-myelinated C fibers. Remember we talked about A, B, and C fibers? A and B were myelinated, they're very fast. Non-myelinated C fibers, all right? Because generally speaking, it doesn't matter whether we're aware of something within 1/10 of a second, remember the different speeds, or whether it takes half a second. That's usually not all that critical, all right? Most are nociceptors and thermoreceptors. So pain and temperature receptors are free nerve endings, all right? Just a dead end in the skin. Vanilloid receptors, a special kind of receptor, responds to heat, low pH, and chemicals like capsaicin, the stuff in chili peppers. So receptors can respond to more than one stimulus. Itch receptors respond to histamine, okay? Remember, neurotransmitter, also involved in the immune response. Tactile Merkel cells respond to fine touch, which is light pressure. Hair follicles, receptors, those respond to hair movement. So see, there are lots of different kinds of things out there, all right? These are all general senses. They all basically are just in one way or another just free nerve endings. And there is the vanilloid receptor right there. Big complex protein, lots of amino acids embedded there in the skin. All right, let's move on, talk about encapsulated nerve endings. So here we have a capsule. Most are mechanoreceptors. They detect pressure. So tactile corpuscles, the Meissner's corpuscles, they used to be called, respond to light touch. Lamellar corpuscles, used to be called Pacinian, respond to deep pressure and vibration. Bulbous corpuscles, used to be called Ruffini endings, respond to deep continuous pressure. Muscle spindle organs and tendon organs respond to muscle stretch and contraction. Joint kinesthetic receptors are proprioceptors in synovial joints. I don't want to make a big deal about these. my main point here is to show you that you have different kinds of receptors that have different specialties. In some cases they can overlap, but they have different specialties and different things that they respond to, and that's why we have such a rich sensory palette of information. All right, we can find differences between lots of different things. That's because we have so many different kinds of receptors sending information to the brain. So cutaneous mechanoreceptors, let's look at, there are 4 basic kinds here. Tactile discs used to be called Merkel discs. Those are for fine touch. They adapt slowly. They're non-encapsulated. Then you have the bulbous corpuscle, used to be called Ruffini. Those are for deep continuous pressure. They adapt very slowly, of course, for continuous pressure. They're encapsulated. Then we have lamellated corpuscles. For deep pressure and vibration, they adapt rapidly, as opposed to the bulbous corpuscle. They're encapsulated. Then the tactile corpuscles used to be called Meissner. Those are for discriminative touch, telling exactly where something is touching you, okay? They adapt very rapidly, and they are encapsulated. You don't have to memorize these. I won't be really nasty and have you tell me exactly what a lamellated corpuscle does versus a tactile corpuscle. Again, my point here is just to try to show you that you have a variety of receptors. So no matter what's happening, you've got different kinds of receptors that are sending different amounts of information. So, a deep something that, when somebody presses really hard on your skin, you will activate both the fine touch receptors and the deep pressure receptors. So your brain will get information from more than one receptor. And your brain then basically carefully sorts out all the information and figures out what's going on. All right? That's why we're so good. Especially, touch sensations. We're very sensitive to various kinds of touch sensations. And it's because we have so many different kinds of receptors. Sensation versus perception. It's time to make a distinction here that at first might not seem important, but it really is. All right? Sensation is different than perception. Right? Let's talk about what they are. Sensation simply means being aware of changes in the internal or external environment. So sensation is basically just detection. You're able to tell that something is happening, okay? This happens mostly out at the receptor level and along the neural pathways. So the receptor is stimulated, it sends a nerve impulse. So from that, your body is aware something is happening out there, okay? Perception, on the other hand, is the conscious interpretation of those things in the cerebral cortex and other brain areas. So perception is basically interpretation, all right? This is happening mostly in the cerebral cortex. So perception means understanding what's happening. It means putting together all the signals and figuring out what's going on. Whereas sensation is just telling that something's going on. So for example, like let's say sensation, here would be an example of sensation. In the distance, I see a white circle. Now the white circle is getting larger. Now the white circle is getting larger. Now it's getting larger. Now it's getting larger. See, perception would be, oh my God, there's a baseball coming right at my head. Okay? Do you get it? Sensation is purely just detection of what it is. Perception is figuring out what's going on and understanding it. Okay? It's a big difference. Notice, not 5 senses. No, many more. At least 14. And just as a reminder, sensory processing typically involves the following. You have stimulation of a sensory receptor by physical energy. So heat, cold, pain, pressure. There is physical energy in the world that's impacting you. Light, sound, those are physical energy. Then transduction. What a wonderful word. Transduction. Trans means across, duct means to lead across. So this is conversion of the physical energy of the stimulus into graded potentials. Think of it this way. When you eat a strawberry, so you put a strawberry on your tongue, your taste buds are now detecting a strawberry. Do you actually have molecules of the strawberry that go into your brain? No, you don't. What has to happen is you have to convert the chemical energy of the strawberry into the electrical energy of a graded potential and then an action potential. And your brain then figures out the action potentials, okay? So that's transduction. That's very important. Sort of a consequence of this, if you think about it for a moment, it means you are never basically aware of direct contact with reality. Your brain has never actually had any strawberry molecules inside of it. It just has a way of interpreting strawberry molecules, all right? That's a philosophical thing. That's actually very profound, but will leave profound for the philosophers, okay? Then we have to generate a nerve impulse after we transduce the stimulus, all right? After we convert the physical energy into nerve energy, then we have to generate the nerve impulse. And so if the graded potentials exceed threshold, an action potential generated along that first order neuron. And then finally in the brain, we have to put it all together. Exactly what's going on here. What's lots of different sensory signals coming into your body. Your brain has to be the one to figure it out. It's like, oh my God, wait, what am I doing? I'm dancing naked on the tabletop, all right? Yeah, that's why it felt so breezy. That's why the bottoms of my feet feel wet, all right? Yeah, so integration of sensory input. So second and third order neurons carry the signal to the cerebral cortex where it is interpreted.